So we're doing more applications of separable differential equations. It turns out that we can use a separable differential equation to model a rocket launch. Got my laser pointer, and here we go. So let's model a rocket launch. We have a rocket. Let's say we launch it from the ground level, and so it starts at y equals 0, you can say. And let's say that the rocket consists of an outer shell, and inside it there's a fuel-air mixture, and the whole thing together weighs m0. During flight, the fuel burns at a constant rate for tau seconds, and exhaust gases are ejected from the bottom of the rocket at this rate, some rate beta kilograms per second at a speed of c meters per second relative to the rocket. So let me skip this picture. So here's a picture of our rocket. It has a certain mass and a certain velocity. We're trying to write a differential equation to describe how the rocket moves. And our strategy for this problem is we're going to use conservation of momentum. So, and we're going to ignore air resistance and assume that gravity is constant. Obviously, assuming gravity is constant wouldn't work if the rocket were going, say, leaving the atmosphere or getting to a significantly large altitude. But if we assume if we're assuming this is a small atmospheric rocket launch where the rocket's only going to go up, say, a few hundred feet or so, then assuming that g is constant is perfectly fine. Now, since the fuel's burning and gases are being ejected from the bottom of the rocket, the mass of the rocket is decreasing at a rate of beta kilograms per second, meaning the total mass of our rocket here is the initial mass minus beta times t. So we fix a time t. We'll fix a time t and consider what happens to the rocket between t and t plus delta t. So during that time interval, delta m gas is ejected from the bottom of the rocket, meaning the rocket now weighs delta m less than it weighed a moment ago. And now we can calculate the total momentum of the rocket plus gas at this moment, and calculate the total momentum of rocket plus gas at this moment. So the momentum here is just mass times velocity. That's the definition of momentum. Here we have to calculate the momentum of the rocket and add the momentum of the ejected gas during that moment in time. So the total momentum of rocket and gas at this time t plus delta t, that's this moment here, this is the momentum of the rocket because it weighs delta m less, but it's traveling delta v faster than it was before. So this is the momentum of the rocket. This is the momentum of the exhaust gas, delta m times v minus c. V minus c is the velocity of the gas because the rocket was initially moving at a velocity v, and we said that the gas is being ejected at a speed c relative to the rocket, meaning the gas is now going c meters per second slower than the rocket. So the velocity of the gas is v minus c. So this is the momentum of the gas that was ejected. You can expand this, cancel things. The v delta m cancels with the v delta m, and you're left with this. There's a tiny typo here. If you want to calculate the change in momentum, it's this expression, the new momentum, minus this expression, the old momentum. I forgot delta m, delta v should have been written right here. So my bad. So this is the change in momentum, meaning change in momentum, which we denote by delta capital P, is equal to this expression. But Newton tells us that the force acting on the rocket and gas is equal to the change in momentum divided by change in time. And since the force acting on the rocket is negative mg, that's the force of gravity pulling down on the rocket, and gas, we have negative mg equals this expression divided by delta t, which I was able to simplify down to this. Let's go to the next slide and see what we can do with this. So force equals change in momentum divided by change in time becomes this equation. And change in mass is just beta times the change in time, because the rocket is ejecting gas from its bottom at a rate of beta kilograms per second. So the amount of mass that the rocket loses during this moment of time is beta times the change in time. That's the amount of gas ejected, so we replace delta m with beta delta t, and we get this. And now we can take the limit as delta t approaches 0 of both sides. The left-hand side doesn't even depend on delta t, so it just remains as negative mg. On the right-hand side, this is approaching 0, so we're just left with m times dv dt minus c times the rate of mass ejection, which we said was just beta. So the rate at which mass is being ejected from the rocket is just beta, so that's what we have. This equals that. So we also said that the mass, m, of the rocket is m naught minus beta t. So we replace that as well, and we now have this. And this is starting to look an awful lot like a differential equation. Rearrange, voila. We have this differential equation for our rocket. Now we're going to solve it. So we have this differential equation. Let's just integrate both sides. So, well, I should say bring the dt over to the right-hand side and integrate both sides. And you get v equals, this is what you get when you integrate. Let's not confuse lowercase c, which represents the speed of the exhaust gas, versus capital C, which is my constant of integration. When I integrate both sides. Now, the rocket started at rest. It started on the ground at rest. So v is 0 when t is 0. So we conclude that plugging in 0 for v and 0 for t, we get that c equals lowercase c log m naught. And we conclude v equals this whole thing. Oops, and then I used rules of logs to bring these two things together as one thing, minus c log this minus gt. So log of, well, you see I used rules of logs here, and I factored out the c. Now, next we know that velocity is the derivative of y with respect to t, so if we integrate, so this is dy over dt, bring the dt over and integrate both sides, and we get that y is the integral of this whole expression, which you can do by hand, or it's kind of annoying because you'd have to use integration by parts to deal with the integral of the log. You'd have to do a u substitution and an integration by parts, which is annoying, or you can just do it by computer. However you prefer. When you evaluate this integral, you get all of this. Don't forget your new constant of integration here. So this is our expression for y. So we did it. if you simplify the expression on the previous slide, you get. It looks like I already found my constant C2, so I guess I skipped that step. But anyway, this is the expression we end up with. And I define this capital M to be m naught minus beta t all over m naught. It's just for convenience. It's called the fractional mass of the rocket. Notice this is the current mass of the rocket, and this is the original mass of the rocket. And so capital M is the ratio of the rocket's current mass to its starting mass. So that's why we call it the fractional mass. And this expression simplifies even further to what you see here. And from the previous slide, we had this equation. So now, if m1 is m naught minus beta tau, remember tau is the moment that the fuel is exhausted. So m1 represents the final mass of the rocket at the moment of burnout. And at that moment in time, we have y of tau equals c tau minus g over 2 tau squared, which is just like projectile motion, really. But then you add this. So this is the height of the rocket at burnout, and this is the velocity of the rocket at burnout. So now we have a specific example. We're going to say that we start with a rocket that weighs 10 kilograms. That's rocket and fuel together weighing 10 kilograms. We're going to suppose that the rocket burns its fuel for 10 seconds. I have no idea how realistic that is, but let's just say that's what it does. Seemed reasonable to me when I was making up the problem. And let's say the exhaust gases are ejected from the bottom of the rocket at 0.6 of a kilogram per second and being ejected at 500 meters per second relative to the rocket. We'll assume gravity is 9.8 meters per second squared, and we're going to try and find the final height and velocity of the rocket at burnout. So using the work from the previous slides, we know that this is the height and this is the velocity at burnout, and these are the numbers of the problem: 500, 4, 10, 10, and 0.6. Plug it all in, and you get 1,455.7 meters and 360 meters per second. So that is the moment that the fuel stops burning. And then if you wanted to know what the rocket did from there, the rocket is now a projectile. When the fuel stops burning, the rocket becomes a simple projectile, and you can use basic physics 1 if you want to know, for example, how much higher the rocket goes after burnout. Now, before we discuss the more interesting topic of launching a rocket with air resistance taken into account, we first need to develop a little bit of theory on solving more complicated differential equations. So far, we've been seeing a ton of applications that boil down to this very simple form. Derivative of y with respect to x is equal to f of x times g of y. These are the separable equations. And now we're finally going to consider a new type of equation with a very different solution technique. So this is the new equation that we're going to be looking at. It's derivative of y with respect to x plus some function of x times y equals another function of x. So p of x and q of x are functions of x, and I'll teach you how you can, in principle, solve any equation in this form. This is called the first order linear equation. Let's discuss that terminology for a moment. First order. Whenever I say that a differential equation is first order, That means it involves only y and derivatives. Or, I'm sorry, only involves first derivatives of y. So a second order equation might involve the second derivative of y, etc. So first order equation has only the derivative of y and y. And when I say it's linear, I don't mean that p of x and q of x are linear functions. What I mean is that it's linear with respect to the dependent variable y, meaning that you don't have anything in here like y squared or y times dy dx. I mean that the equation depends linearly on y and y prime. So that's what's meant by linear when talking about differential equations. So this is just what I said. So p and q can be any reasonable function that you can think of. So here's a problem from Edwards and Penny. That's the textbook that I learned differential equations from way back when. So solve this differential equation. I usually don't like to do problems like these that don't have any physical motivation, but I found this was a pretty good example, so we will do it. So we can rewrite this equation in first order linear form. First of all, we can call y prime dy over dx. And you bring this y cosine x over to the left-hand side, and then you have cosine x on the right-hand side. This is a first order linear equation where p of x is cosine x. That's p. That's q is also cosine x. Notice that if you have these definitions of p of x and q of x, then the equation does become this, which is the definition of a first order linear equation. Anytime you want to solve an equation like this, the first step is to multiply both sides by an integrating factor. And this is the integrating factor. It's defined as a function of x. It's called I of x. And we always do the same thing. We take e to the integral of p of x dx. You just kind of memorize that. That's a thing. We do that. So we do that. And in this problem, p of x is cosine x. So this is e to the integral of cosine x, which is e to the sine x. Fun fact, when you're doing this integrating factor calculation, you do not need to worry about the constant of integration. So you can just take sine x. If you add a constant, it doesn't help or hurt you. You just don't need to do it. Now, if you so again, I said we're going to multiply both sides by the integrating factor. This here is the integrating factor, so I'll multiply this equation by the integrating factor, and we end up with all of this. E to the sine x y prime plus cosine x e to the sine x y equals this. And the whole point of multiplying by the integrating factor, this left-hand side looks horrible, and you might be asking at this moment why in the world we did such an awful thing to the left-hand side. But something wonderful happens. The left-hand side is this. This takes some getting used to, so take a moment to stare at it. And while you're staring at it, let me help you. What we have here is a product of two things, e to the sine x times y. If you take the derivative of it, then by the product rule, you get e to the sine x y prime plus the derivative of e to the sine x times y, which is what you see here. So, again, the derivative of this, the derivative of what's in here is equal to what you see here by the product rule. So we were able to rewrite this whole thing as the derivative of a product. That is why we did the integrating factor. It turns out you can always do this. So don't think that we were just being especially clever for this problem. All first-order linear equations get solved the same way. You multiply by an integrating factor, and then this miracle happens. So you do that. And now if we integrate both sides with respect to x, well, the integral of a derivative is just the thing itself. So on the left-hand side, we just have e to the sine x times y. Now we still have to integrate the right-hand side, so we have to do that. But that's a pretty easy integral. If you just do u equals sine x, then cosine x dx is du. So you can pretty quickly get e to the sine x plus c. Now divide both sides by e to the sine x. And we have y equals 1 plus c e to the minus sine x. Again, I just took this and divided both sides by e to the sine x. And finally, we use the initial condition y of pi equals 2. So 2 equals 1 plus c e to the negative 0, what you see here, which is 1 plus c, so c is 1. And we conclude that this is the solution to the problem. As illustrated, all you have to do to solve a first-order linear equation, well, to begin is you multiply by the integrating factor. So you start here, then you multiply both sides by I of x, and you have this more complicated looking expression. The wonderful thing about the integrating factor, and I encourage you to check this, is that the derivative of I of x is equal to p of x I of x. Seriously, try it. It's true. Just use the chain rule and the fundamental theorem of calculus to calculate the derivative of this thing. And therefore, the left-hand side can now be rewritten using the product rule. d dx of I of x times y. And I encourage you to check this as well, that when you apply the product rule, you get yi prime plus iy prime. Using the fact that I prime is pi, you get precisely what you have here. So this left-hand side equals this left-hand side. So this is just, we're taking this and rewriting it using the product rule and this observation. Integrate both sides with respect to x, and divide both sides by I of x. And that is the general solution to one of those problems, to a first-order linear equation. I generally don't recommend that students bother memorizing this. It's really better if you understand the process of how you get here. So you understand that you're supposed to calculate an integrating factor, multiply, recognize a product rule, integrate, and divide. It's really the process that you want to know rather than the final formula. This brings me to another interesting application that I want to cover before we get back to rockets with air resistance, which I think I'll put off till the next video. So we'll finish with this. We have a tank that contains 60 gallons of pure water, and then we have salt water being mixed into the tank at a rate of 2 gallons per minute, where we have a pound of salt per gallon as the concentration. And then the tank is being mixed, and perfectly mixed solution is leaving the tank at 3 gallons per minute. And then that means that the tank is empty after exactly 1 hour, because we have 1 gallon per minute in net total leaving the tank. And since there are 60 gallons originally in the tank, it takes an hour to drain. So we're going to find the amount of salt remaining in the tank, in pounds that is, after t minutes. and figure out the maximum amount of salt ever in the tank. Now, if that problem doesn't make sense to you yet, here's a picture for you. So the tank started off full, and what's happening is salt water is, not only did the tank start off full, it started off with 60 gallons of pure water. So this was full of pure water, 60 gallons. Water starts entering 2 gallons per minute with a lot of salt in there. So it's very salty water that's entering. It mixes into the tank, and the mixed solution is exiting at 3 gallons per minute. So the tank is draining from 60 down to 0, and I'm curious to know how much salt is ever in the tank at any moment in time. And part B asks, what's the maximum amount of salt ever in the tank? So let's go about trying to answer this question by modeling it with the differential equation. So notice that the volume of water in the tank, which I'll denote by V, is equal to 60 minus T, because, as I said before, volume of water is being lost at a rate of 1 gallon per minute, since it's entering at 2 and exiting at 3. Next, let A of T denote the amount, A is for amount, of salt in pounds in the tank at time T, in minutes. And then try to stay with me here. The concentration, when I say concentration, I mean pounds per gallon. So the concentration, which I'm going to denote by lowercase c, of salt is equal to the amount of salt divided by the amount of water in gallons. But the amount of salt is just A of T, and the amount of gallons of water in the tank is 60 minus T. So we're left with A of T over 60 minus T pounds of salt per gallon. That's the concentration at any moment in time. Thus, the salt is leaving the tank. Since the tank is being emptied at a rate of 3 gallons per minute, salt is leaving the tank at a rate of 3C. So, because there's 3 gallons leaving per minute, and C is the concentration of salt in those exiting gallons. So this is the rate that salt is leaving. On the other hand, salt is entering the tank at a constant rate of 2. And I got these units wrong. I apologize for that. Salt is leaving the tank at this rate in pounds per minute, and it's entering the tank 2 pounds per minute. There are 2 pounds of salt entering the tank per minute, and this many pounds of salt leaving the tank per minute. So we have a differential equation. The rate at which the amount of salt in the tank is changing is equal to the rate at which salt is entering the tank minus the rate at which salt is exiting the tank. We said that salt is entering the tank at 2 and exiting the tank according to this expression. This is the rate salt is exiting the tank. Rewrite this a bit. We have dA dt plus 3 over 60 minus TA equals 2. And this is a first order linear differential equation where P of t is what you see here and Q of t is just 2. Multiply both sides by the integrating factor. That's how we solve first order linear equations. The integrating factor is e to the integral of P of t, which is that. The integral is negative 3 log 60 minus t, which, so e to the log of 60 minus t is just 60 minus t, all raised to the negative 3 power. So that's 1 over 60 minus t cubed. So we have, when we started with this was our integrating factor, and we multiplied both sides by it to get this kind of nasty looking equation. But don't be intimidated by it. It's there's nothing wrong. We just multiplied by the integrating factor, and now the left hand side is the derivative of a product, as always. This is it. The left-hand side is just the derivative of IA. And so we integrate both sides, and we get this. We have an arbitrary constant of integration C. And since we know that the tank started with pure water, so the amount of salt in the tank at time 0 was 0. So we plug in 0 for T and 0 for A, and we conclude that C is -1 over 3,600. And this is our final expression for the amount of salt in the tank after T minutes. This is it. So we have our expression, and now we want to know when the maximum amount of salt occurred. So we have an expression for A. This is just a Calc 1 problem. So time is going from 0 to 60 because the tank is empty after 60 minutes. And to find the maximum of A, we just set the derivative of A with respect to T equal to 0. If you remember that from Calc 1. And this is the derivative of A with respect to T. Set it equal to 0. Solve for T. And we find that T is either 25.4 or 94.6. That's just expanding this and using the quadratic formula. But that's not... 94.6 doesn't make any sense because the tank is empty after 60 minutes. So this must be the correct answer. So the tank is, so we conclude 25.4 is the maximum, is the time at which the maximum occurs. Plug that back into A of T. A of 25.4 is 23.09 pounds. So the maximum amount of salt ever in the tank is 23.09 pounds. And here's a picture of the situation. So the salt concentration started at 0, and the salt water poured into the tank reached a maximum. But of course, after 60 minutes, the salt amount was back to 0 because the tank was empty. So the maximum had to occur somewhere between 0 and 60, and we just found it occurs here around 25 seconds, and this was the maximum amount of salt.